Welcome to the deep dive. Today, we are undertaking a very specific mission.
Oh, yeah.
We're going to dissect what is, well, arguably the single most important academic paper in the history of modern computing.
Okay, bold claim. Which one?
Forget white papers, forget manifestos. We are diving deep into Attention is All You Need.
Ah, right. Sounds like a mindfulness retreat title or something.
Doesn't it? But no, it's actually the blueprint for pretty much every generative AI tool you use today. ChatGPT, image generators, all of it.
Absolutely. That paper, June 12th, 2017, right? It
Yeah.
wasn't just an improvement. It completely changed the fundamental architecture of how we build these AI systems.
Exactly. So our goal today is to give you, our listeners, a real shortcut to understanding the foundational tech, the stuff that makes this whole AI revolution, well, possible.
Makes sense. Where should we start?
Let's start with the core idea, the elevator pitch. Why is this paper the one? What's so profoundly important about it?
Okay. Well, the core insight is kind of hinted at in the name, right?
Yeah.
But technically, it introduced the transformer model.
Right, the transformer.
And the revolution was systemic.
Yeah.
It basically threw out the decades-long reliance on sequential models, things like recurrent neural networks, RNNs, and even CNNs for sequence stuff.
So it just got rid of them for language tasks.
Pretty much, yeah. For sequence-to-sequence tasks specifically, which was the initial focus, it showed you didn't need that step-by-step recurrence.
And by doing that, this new architecture, it unlocked the ability to train these absolutely massive models with hundreds of billions of parameters.
Something totally impossible just months before.
Exactly. It feels like this is the pivot point where AI stopped thinking one word at a time sequentially and started thinking, well, in parallel.
That's a great way to put it.
Yeah.
This shift from relying on sequence step by step to this parallelized attention mechanism that's the single architectural decision that enables the scale and power of modern LLMs. Your Geminis, your Claudes, all of them.
Okay, so before 2017, you mentioned RNNs were king for sequence tasks. Things like machine translation, right? Taking an English sentence, turning it into German.
Yeah, they were the standard. Sequence transduction tasks, that was their domain.
But they had these inherent, almost crippling limitations. Let's dig into those. What were the structural weaknesses?
Well, the biggest problem was that sequential processing itself. An RNN, or even the fancier ones like LSTMs, long short-term memory, or GRUs.
Right, the gated ones.
Yeah. They all worked kind of like someone painstakingly transcribing a lecture word by word. Each calculation, each step, depended entirely on the result of the step right before it.
Okay, so if you're translating a really long sentence, maybe 500 words long,
Yeah, a complex one.
the model has to process word 1, then wait. Then word 2, wait again. All the way to word 500, always waiting.
Exactly. And that serial dependency created two huge problems.
Okay, what's the first one?
The first is often called the vanishing gradient problem. Basically, it means that the influence of words early in a long sequence just kind of fades away. It functionally disappears by the time the model gets to the end.
So the context gets lost.
Totally lost.
Huh.
If the main subject of your sentence is way back in the first 10 words, and the verb that relates to it is like 300 words later, the model might mistranslate that verb because it's effectively forgotten the subject's details, gender, number, whatever.
Yeah.
Long-range dependency was really, really brittle.
Okay, that's a major context issue. And the second failure, you mentioned that, was about scale and speed.
Right, and this is where the transformer really just blew the doors off. The sequential nature was a fundamental bottleneck for training.
How so?
Because the computation was step by step, you couldn't really take advantage of modern parallel computing hardware. GPUs, graphics processing units, they are amazing at doing millions of simple, identical calculations all at the same time.
Right, parallel processing is their strength.
But RNNs couldn't leverage that. Their structure wasn't parallelizable. So training them was slow, it took tons of resources, and it just didn't align with where hardware was going.
Yeah.
Researchers were stuck with smaller models and much longer training cycles.
Okay, so here comes the transformer in 2017. It arrives and basically solves both these problems, the context problem and the speed problem, by just flipping the whole process around.
Exactly. It shifted the core assumption. Instead of sequence matters most, the transformer said, actually relationship matters most.
Relationship between words, you mean?
Yeah. The breakthrough was achieving this kind of global, simultaneous understanding. Instead of waiting for word 1, then word 2, the transformer figures out the contextual meaning for all the words in the input sentence at the exact same time.
Simultaneously.
Simultaneously. And that is a total game changer for efficiency. It allows for immediate, massive parallel computation across huge arrays of GPUs.
So going back to that metaphor, instead of reading a scroll 1 inch at a time, the transformer basically lays the entire scroll out on a giant table and instantly sees how every single word on that scroll relates to every other word.
That's a perfect way to frame it. And the magic trick enabling this, it's the complete reliance solely on this thing called the attention mechanism, specifically self-attention.
Right, the attention is all you need part.
That's it. It's not about remembering things over time like an RNN tries to do. It's about weighing the relevance right now of every single piece of the input to every other piece. It's dynamic, it's interconnected, it's instantly contextual.
And that directly paved the way for training these enormous models efficiently, orders of magnitude bigger than anything before.
Absolutely.
Okay, so this transformer architecture sounds complex, but the paper actually builds it on 3 surprisingly clean, elegant ideas. Let's dive into those pillars, starting with the absolute heart of the model, the self-attention mechanism. You hear this QKV acronym thrown around a lot.
Right, QKV.
Yeah.
Self-attention is that dynamic process we just talked about, the one that assesses all those relationships simultaneously. So for every token, which is basically a word or maybe part of a word that goes into the transformer, the model generates 3 distinct vectors, just lists of numbers, really. These are the query Q, the key K, and the value V.
Query key value.
Okay.
You mentioned before it's like a database lookup, but can we get a bit more into the mechanics? What's actually happening with these Q, K, and V vectors?
Sure. So imagine the model wants to understand a specific word better, get its contextualized meaning. It takes that word's query vector, the Q,
Okay.
and it compares that query vector against the key vector, the K, of every other word in the entire sequence, including itself, actually.
How does it compare them?
Typically, it uses a mathematical operation called a dot product. Especially in high dimensions, a dot product is a really good way to measure similarity or relevance. How aligned are these 2 concepts, represented by the vectors?
So a higher dot product means those 2 words are more related, semantically or grammatically or somehow.
Exactly. It captures that relevance. Now, this raw similarity score is important, but there's a step first. Usually these scores are scaled down a bit.
Scaled. Why?
Often they divide by the square root of the dimension of the key vectors. It sounds technical, but it basically stops the dot product values from getting too huge, which could make the training unstable later on. It just helps keep things smooth.
Okay, so we have these scaled similarity scores between our query word and all the keywords. What's next?
Next, these scores get fed into something called a softmax function.
Softmax. I've heard of that.
Yeah, it's common in machine learning. What softmax does is it takes all those similarity scores and turns them into normalized weights. Basically, percentages that all add up to 1 or 100%.
Ah, okay, so it tells the model for this one query word.
Right. For this specific word you're focusing on, here's the exact percentage of attention or focus or weight you should give to every single word in the sequence, including itself.
And then finally, those percentage weights get applied to the 3rd vector, the value vectors.
Yes. The final output, the new context-rich representation for our original query word, is simply a weighted sum. You take all the value vectors from the entire sequence and you weight each one by the attention score, the percentage we just calculated with softmax.
Yeah.
Then you add them all up.
Okay, let me try an example. If the sentence is, the financial bank failed due to fraud, when the model processes the word bank, its query vector is going to look for related keys, right? So its Q vector for bank will probably have a high dot product, a high similarity, with the K vectors for financial and maybe failed and fraud.
Exactly. Because contextually, those words are highly relevant to understanding which kind of bank we mean, not a riverbank.
Right. So the value vectors for financial, failed, and fraud get higher weights from the softmax.
All right.
And those values are then strongly incorporated, added into the final representation of bank, making it clear it's a financial institution in trouble.
Precisely. And the absolute genius part is that this whole process, querying, comparing keys, getting weights via softmax, summing up values, happens simultaneously for every single word in the input sequence. In parallel.
Ah, that's the key. That's how it gets that long-range understanding that RNNs struggled with.
Absolutely. The connection between bank and fraud, even if they were separated by dozens of words, is established instantly. Self-attention fundamentally broke through the memory limitation of the older architectures. Okay, that's pillar 1, self-attention, powerful stuff. Now, pillar 2, multi-head attention. So one attention mechanism gives context, but the paper said, no, we need multiple attention heads. Why? Why more than one?
Yeah, it's about getting a richer, more multidimensional understanding. Think of a single self-attention mechanism, what we just described, as maybe learning to focus on one specific kind of relationship. Maybe it gets really good at spotting subject-verb agreement, for instance.
Okay, like one specialist. Exactly. But language is complex. There are lots of different relationships happening at once. So with multi-head attention, you run, say, 8 or 12 or 16 of these self-attention mechanisms in parallel. Each one is called a head.
And they're all looking at the same input sentence.
Yes, but crucially, each head learns to focus on different things. They develop specializations.
So they aren't just redundant, they're finding different kinds of patterns.
Precisely. And we actually see evidence of this when we analyze trained models. One head might become really good at tracking syntactic relationships, like, okay, this noun is the direct object of this verb. Another head might specialize in those tricky long-distance dependencies we talked about, maybe linking a pronoun like it back to the specific noun it refers to from several sentences ago.
Okay.
And maybe a third head gets good at capturing something more subtle, like the overall tone or sentiment of a phrase.
Right, so it's like having a committee of linguistic experts, each looking at the sentence through their own specialized lens.
That's a great analogy. And then the model combines the outputs from all these different heads. It concatenates them and processes them a bit more. The final representation for each word becomes incredibly rich because it's informed by all these multiple specialized perspectives on grammar, context, meaning.
And that boosts performance on all sorts of different tasks, right?
Significantly. It moves beyond just a general "is this related" score to a much more structured, nuanced understanding of how language actually works.
Okay, that makes sense. Now for the third pillar. This one addresses a kind of side effect of all this parallel processing, positional encoding. If you process everything simultaneously, you lose the order, right? How does the transformer know the cat chased the dog is different from the dog chased the cat? RNNs got that for free because they were sequential.
That's a critical point. The parallel architecture, by its nature, throws away the inherent sequence information. If you just fed the word embeddings into self-attention, it'd be like processing a bag of words. You'd know what words were there, but not where.
Which would destroy grammar.
Completely.
Yeah.
So they needed a way to inject the position information back into the model mathematically.
And the paper solution used those interesting periodic functions, sine and cosine waves. Why those? Why not just, number the words? Position 1, position 2, position 3, and add that number.
That's a good question. Using simple integer labels like 1, 2, 3, well, it doesn't scale very well. The numbers could get huge, and more importantly, the model might struggle to generalize to sequences longer than any it saw during training. It wouldn't know what position 501 means if it only saw up to 500.
Okay.
The genius of using sine and cosine functions of different frequencies or wavelengths is kind of twofold. First, they generate a unique code, a unique vector, for every single position.
So position 5 has a different code than position 6.
Yes. But second, and this is the really clever part, because of the mathematical properties of these waves, the relationship between positions remains consistent. The model can learn, through simple linear transformations, to figure out the relative distance between any two positions.
So we can learn that position 15 is, say, 5 steps away from position 10 without needing to memorize the absolute positions 10 and 15.
Exactly. It learns relative positioning. And understanding relative positions, what comes before what, how far apart things are, is absolutely essential for grasping grammar and syntax.
So how does this work in practice? These sine and cosine calculations generate a vector, a positional encoding vector.
Yep, a vector the same size as the word embedding vector.
And you just add it to the word's own meaning vector, the embedding.
Correct. You literally just add the two vectors together. So the input that actually goes into the first transformer layer for each word contains both the semantic meaning of the word from its embedding and its position in the sequence from its positional encoding.
Wow. So the self-attention mechanism then inherently uses both meaning and position when it calculates those relevance scores.
Precisely. Without positional encoding, the transformer would be powerful but fundamentally illiterate. It wouldn't understand order, which is critical for language. It solves the problem created by ditching recurrence.
Okay, the architecture is elegant. Self-attention, multi-head attention, positional encoding. It sounds good in theory, but, it wouldn't have caused a revolution if it didn't actually work better. Let's talk results. What were the numbers that made the research community sit up and take notice immediately?
Right, the proof is in the pudding. The transformer was initially designed and tested primarily on machine translation tasks. And it didn't just nudge the state of the art, it pretty much smashed it on the standard benchmarks used at the time. Specifically, the WMT 2014 translation tasks.
WMT 2014. And the main metric they use for translation quality is BLEU score, right? Bilingual Evaluation Understudy.
That's the one. It's not perfect, but it was the standard. It basically measures how much the machine's translation overlaps with one or more high-quality human translations. Higher is better.
So what were the scores? Let's put them in context.
Okay, on the English to German translation task, the transformer model presented in the paper achieved a BLEU score of 28.4.
And how good was that compared to what existed before?
It was a significant jump. The best models before that, usually complex RNNs or sometimes convolutional approaches, were typically hovering around maybe 26, 27 BLEU points. So 28.4 was a clear, measurable leap in translation quality.
Okay, a solid win. And what about the other main task, English to French? That one's often considered a bit easier, but still a key benchmark.
Right. On English to French, the gap was even more impressive. The transformer hit 41.8 BLEU.
Wow, 41.8. How did that compare?
Again, it comfortably surpassed the previous state-of-the-art models. But here's the kicker, the really crucial part. It achieved these better scores while training dramatically faster and using less computation overall during training.
Ah, that dual victory. Better quality and much more efficient to train.
Exactly. That combination is what instantly cemented it as the new gold standard architecture. People realized this wasn't just another incremental improvement.
Let's focus on that efficiency aspect for a moment, because that feels like the real key that unlocked everything that came later. The parallel design, how much faster was it compared to the old sequential RNNs?
It was a night and day difference. The paper specifically mentioned that their big transformer model reached that state-of-the-art BLEU score after training for just 3.5 days on 8, high-end GPUs at the time.
It's 3.5 days. And the older systems.
Complex RNN or LSTM models for similar high-performance translation tasks could often take weeks, sometimes even longer, depending on the specifics. The parallel nature of the transformer just made it vastly more suitable for modern hardware.
And that speed isn't just convenient, it's transformative for research and development, right?
Absolutely critical. Faster training cycles mean researchers can iterate much more quickly. They can try out new ideas, tweak hyperparameters, test different data sets.
And crucially, it makes scaling feasible.
That's the big one. If your model takes 3 weeks to train, even attempting to train a version that's, say, 100 times larger is practically unthinkable. It would take years. But if your baseline is 3.5 days, suddenly training much, much larger models becomes computationally plausible. The transformer basically gave researchers the computational permission slip they needed to start thinking really big.
It removed the architectural bottleneck that had been holding back progress in natural language processing for years.
Pretty much, yeah. This one, elegant paper, effectively replaced decades of incremental work on RNNs and CNNs for language, and it immediately set the stage for the next era, the era of large-scale generative AI.
Okay, so success in translation was the first big win. But the transformer's architecture, especially that self-attention mechanism for handling long-range context, it turned out to be perfect for more general language understanding. And that leads us directly to the GPT series, right? Generative pre-trained transformers.
The name says it all, doesn't it? GPT. The connection is absolutely direct and foundational. The transformer's main advantages, that deep contextual understanding from self-attention and the massive scalability from parallelization, were precisely the ingredients needed to build models that could learn from, well, practically the entire internet.
Let's really underline that scalability point again. How did processing data simultaneously, in parallel, allow that jump from models with maybe millions of parameters to ones with hundreds of billions?
It comes down to how you utilize the hardware. With a sequential process like an RNN, you're always limited by the speed of that single step-by-step calculation path. Adding more processors doesn't help much beyond a certain point.
Right, the bottleneck remains.
But with a parallel process like the transformer self-attention, you can effectively divide the workload. If you have 1,000 GPUs in a cluster, you can split the computation across all of them and get the results much, much faster. The architecture scales beautifully with more hardware.
So doubling the model size didn't necessarily mean doubling the training time, or worse.
Exactly. While the total amount of computation obviously increased, the actual time it took to train increased much less dramatically than it would have for an RNN. This architectural alignment with modern distributed computing hardware gave researchers the confidence to just keep pushing the parameter counts higher and higher, way beyond what anyone thought was feasible just a year or two earlier.
And this architectural shift arrived just as the idea of transfer learning was really taking hold in NLP. Can you explain that two-phase GPT process, the pre-training and fine-tuning?
Yeah, transfer learning was the other key piece of the puzzle. It works in two main stages. Stage one is this massive, unsupervised pre-training.
Unsupervised meaning no specific labels.
Right. You just feed the transformer architecture enormous amounts of raw text. Terabytes of data from books, articles, websites, code, basically a huge chunk of the internet.
Yeah.
The model's task during this phase is usually very simple, like predicting the next word in a sequence.
Just predicting the next word over and over again on billions of examples.
Exactly. And by doing just that on that massive scale, the model implicitly learns an incredible amount about language, grammar, syntax, semantics, facts about the world, common sense reasoning, different styles of writing. It builds this incredibly rich, general-purpose understanding of human language. It becomes like a universal language prediction engine. Okay, so it develops this core linguistic foundation. Then what's phase two? Phase two is fine-tuning. You take that powerful pre-trained model, which already understands language deeply, and you adapt it for a specific task you actually care about. Maybe text summarization or sentiment analysis or writing chatbot dialogue.
And you use smaller labeled data sets for this part.
Much smaller, yeah. Datasets specifically designed for that task. Because the model already has the core intelligence from pre-training, you only need to give it a relatively small nudge, a small amount of task-specific data to make it perform really well on that particular job. You're transferring the general knowledge to the specific task.
Instead of training a whole new model from scratch for every single application.
Exactly. It's vastly more efficient.
Okay, let's map this onto the timeline of the GPT models because the scaling is just wild. It kicks off with the original GPT in 2018.
Right, GPT-1. That first one really just established the paradigm. It proved that this combination transformer architecture, massive unsupervised pre-training, followed by fine-tuning, actually worked. It showed you could get genuine intelligence transfer.
Then just 1 year later, 2019, we get GPT-2.
Yep, and the scale jump was significant. GPT-2 hit 1.5 billion parameters. This was the model that started to really capture the public's imagination, even though OpenAI initially hesitated to release the full version due to concerns about misuse.
Because it was starting to generate really coherent text.
Astonishingly coherent. Long passages of text that sounded plausible, sometimes even creative. It showed that scaling up the transformer wasn't just making it slightly better at predicting the next word, it was unlocking qualitatively new capabilities.
Okay, then the really big one hits in 2020, GPT-3.
Yeah, GPT-3 was a monster, a landmark model. It jumped to 175 billion parameters, 100 times bigger than GPT-2, roughly.
175 billion. And that scale led to something unexpected, right? This idea of emergence.
Exactly. At that massive scale, GPT-3 started demonstrating abilities it wasn't explicitly trained for. Things like few-shot learning. You could give it just a couple of examples of a task in the prompt, and it could figure out how to do it. Or even zero-shot learning. Just describe the task in natural language, and it could often make a reasonable attempt.
Like it was starting to generalize in a more human-like way.
It certainly hinted at something like that. It suggested that sheer scale, enabled by the transformer's parallel architecture, was unlocking deeper reasoning abilities.
Okay, so GPT-3 was incredibly powerful, but the moment AI really exploded into public consciousness was late 2022 with ChatGPT. That wasn't just GPT-3 though, was it? It was fine-tuned differently.
Right. ChatGPT was built on a model from the GPT-3 series, often referred to as GPT 3.5. But the key difference was how it was fine-tuned. They used a technique called reinforcement learning from human feedback, or RLHF.
RLHF, that sounds important. Why was that necessary? GPT-3 was already smart.
It was smart, but it was also kind of wild. Raw foundation models like GPT-3 can be brilliant one moment, and then generate nonsensical, biased, or even harmful content the next. They don't inherently understand human intent or conversational norms. RLHF was the process designed to make the model more helpful, honest, and harmless, to align it with user expectations.
Okay, can you walk us through RLHF? How do you use human feedback to tame this giant AI?
Sure. It's typically a multi-step process, building on top of that already pre-trained GPT 3.5 model. Step one is usually supervised fine-tuning, SFT.
Okay.
Here, human labelers are hired to basically write conversations. They write example prompts a user might give, and then they write high-quality ideal responses that the chatbot should give. Safe, helpful, following instructions well. You fine-tune the base model on these examples.
So you're basically teaching it the desired style and how to follow instructions, giving it a basic, polite assistant personality.
Exactly. That sets the foundation. But then comes the reinforcement learning part. Step 2 is reward modeling.
Reward model.
Yeah. You take the SFT model and have it generate several different possible responses to a given prompt. Then, human labelers look at these different responses and rank them from best to worst. Which one is most helpful, safest, most accurate?
Okay, so humans provide preference data.
Right. And then you train another separate AI model, the reward model, on this human preference data. The reward model learns to predict which kind of response humans are likely to prefer. It essentially becomes an automated judge of response quality.
So the reward model acts as a stand-in, a proxy for human judgment.
Precisely. And that leads to step 3, the reinforcement learning RL phase itself. You use an RL algorithm, often something called proximal policy optimization or PPO,
Okay.
and you use the reward model to guide the training of the original chatbot model, the SFT model. The chatbot generates responses, the reward model scores them based on predicted human preference, and the RL algorithm updates the chatbot to try and maximize that reward score.
So instead of just predicting the next word, it's learning to generate responses that the reward model thinks humans will like.
Exactly. It's optimizing for helpfulness, honesty, and harmlessness, as judged by the reward model, which was trained on actual human preferences. This whole RLHF loop is what turns the raw power of the GPT 3.5 engine into the useful, engaging, and generally much safer conversational agent we know as ChatGPT.
Wow, that's quite a process. And the result of all this, built entirely on that Transformer Foundation from 2017, it was instantaneous public adoption.
Unprecedented. It really democratized access to powerful generative AI. The growth was just staggering. ChatGPT hit 100 million active users within just 2 months of its launch.
Fastest growing software application in history, right?
By far. And that explosive growth, that ability to serve millions of users simultaneously, goes right back to the scalability and parallel processing power inherent in the transformer architecture laid out in that 2017 paper. It's the invisible engine behind the phenomena.
It's easy to just think transformer means text, like ChatGPT. But you mentioned earlier its core idea, self-attention, is more universal. It's about mapping relationships in any structured data. That versatility seems huge.
It really is. That's probably the ultimate testament to the genius of the architecture. It was born from machine translation, sure, but the core concept proved applicable to almost any task where understanding context and relationships within structured data is important. It didn't matter much what the data was.
Okay, so beyond translation, where else did it make immediate waves within NLP, within language tasks?
Pretty much across the board for classical NLP tasks. We saw big jumps in text summarization. Self-attention is perfect for identifying the most salient sentences or phrases scattered throughout a long document and understanding how they relate to form a coherent summary.
Makes sense. What else?
Question answering. The ability to precisely map the relationship between the words in a question and the words in a potential answer passage in a document was a huge improvement. Finding the exact answer span became much more accurate. And also things like sentiment analysis. Understanding whether a review is positive or negative often depends on subtle context, like negations or intensifiers located elsewhere in the sentence. Self-attention could weigh the importance of those contextual clues much better than previous models.
Okay, so it dominated traditional NLP, but then, crucially, it jumped domains entirely. You mentioned vision transformers, VITs. That seems like a massive leap, going from sequences of words to grids of pixels.
It does sound like a huge leap, maybe even magic.
Yeah.
But conceptually, the adaptation was surprisingly elegant. For decades, the standard for computer vision had been convolutional neural networks, CNNs, which use filters to scan images for patterns.
Right. CNNs were dominant.
VITs basically said, what if we treat an image like a sentence? They take the image, chop it up into a grid of small, usually non-overlapping patches. Think of like 16 by 16 pixel squares.
Okay, so you turn the image into a sequence of patches.
Exactly. Each patch is treated like a token, just like a word in a sentence. You then feed this sequence of image patches into a standard transformer architecture, complete with self-attention.
So instead of the model asking, how relevant is the word financial to the word bank?
Yeah.
The vision transformer is asking, how relevant is this image patch containing, say, a bit of furry ear to that other patch containing a whisker?
Precisely. It learns the spatial and contextual relationships between different parts of the image simultaneously, using the exact same self-attention mechanism. It figures out how different visual components relate to form, objects, and scenes.
And this actually worked. It challenged CNNs.
It worked incredibly well, very quickly matching and sometimes exceeding the performance of state-of-the-art CNNs on major image recognition benchmarks. And it turns out this approach is fundamental to many modern visual AI systems. If you've used tools like Midjourney or DALL-E or Stable Diffusion to generate images, the way those models understand how to compose images, how visual concepts relate, often relies heavily on transformer-based architectures operating on visual tokens. That core DNA is there.
Wow. So the same fundamental idea, parallel self-attention, is now driving cutting-edge text generation, sophisticated code completion in tools like Copilot, and advanced visual understanding and creation. It really is like the invisible operating system for so much of modern AI.
Its influence is just pervasive. You look at any major contemporary AI system, Google's Gemini, which is multimodal, Anthropic's Claude, OpenAI's GPT series, all the big image models code generation tools, they all have the transformer architecture or variants of it running deep in their core. It's what enables this large-scale pre-training and increasingly this cross-modal reasoning where models can understand and connect information from text, images, audio, all within a unified attention framework.
That connection to public interest you mentioned is fascinating, too. Looking at the Google Trends data for the phrase, attention is all you need, it maps perfectly onto the story, doesn't it?
It's a really striking visual record. You look at the period from, say, 2010 to 2016 before the paper. Search volume, basically zero, flat line. It was a concept maybe discussed in a few research labs, completely unknown otherwise.
Right, obscure. Then the paper drops in mid-2017.
And you see a tiny, tiny blip in 2017 and 2018. Barely noticeable. That's the initial academic ripple, probably just researchers at NLP conferences looking it up.
Okay. But then it starts to climb more steadily.
Yeah, from 2019 to 2021, you see this gradual, steady growth. It's still niche, but it's clearly gaining traction. This likely reflects the period where transformers started being adopted more widely in industry. Google released BERT. Other companies started building transformer-based products. It was proving its commercial value.
And then comes late 2022, the ChatGPT moment.
And the graph just goes vertical. A huge hockey stick spike starting in late 2022 and continuing strongly through 2023 and 2024.
Reflecting mainstream awareness.
Totally. Suddenly, millions of people weren't just hearing about AI, they were interacting with it daily via ChatGPT. And as they got curious about how it worked, they started searching for the underlying concepts, and that led them back to the source paper. It's a rare case where a fairly technical academic paper title becomes a mainstream search term because its application literally changed the world overnight.
It's really important, I think, to pause and remember this wasn't just an algorithm appearing out of nowhere. This was the work of 8 specific researchers at Google Brain and Google Research, a real collective effort.
Absolutely. 8 authors on that paper. And what's almost as fascinating as the paper itself is what happened next to many of them. It ties into this narrative sometimes called the Great AI Exodus from Google.
Right. They essentially built the foundational tool, and then several of them left to build companies based on it.
Exactly. They knew firsthand just how revolutionary the transformer was, and many decided to take that knowledge and build the future elsewhere, often competing directly with their former employer.
Let's talk about some of the key figures. Ashish Vaswani is listed as the first author. What was his main contribution?
Vaswani is often credited with really driving that core conceptual leap, the idea of completely replacing the recurrent mechanism with self-attention. His deep understanding of the limitations of sequence modeling pointed towards this radical simplification that, counterintuitively, unlocks so much power and efficiency.
Okay, the central idea. Then there's Noam Shazir. He was already known for work on large-scale systems, right?
Yes. Shazir had a background in making massive machine learning models work efficiently, especially things like mixture of experts models. His expertise was crucial for ensuring the transformer's mathematical formulation was sound, and critically, that it could actually be scaled up effectively during training.
And his later path is really interesting.
Very direct. He left Google and co-founded Character.ai.
Character.ai, yeah. Focused on personalized chatbots.
Exactly. Building highly engaging, persona-driven conversational agents. A business that relies entirely on the transformer's ability to handle deep, stateful, nuanced dialogue, which goes far beyond simple Q&A.
We should also mention Nikki Parmar and Ukas Kaiser. They were also key authors.
Definitely. Karmar played a crucial role in the model's design details, particularly around the attention mechanism and ensuring the overall training process was stable and reproducible. Getting these large models to train reliably is a huge challenge.
Right. And Kaiser.
Kaiser was instrumental on the implementation side. He was one of the main creators of the TensorTo-Tensor library at Google.
Ah, the software library?
Yeah, TensorTo-Tensor was the practical framework, the toolkit that actually allowed them and others at Google to build and train these complex transformer models effectively. It bridged the gap between the theoretical paper and working code running on Google's hardware.
And Jacob Uskrey. He had a more senior role.
Yes, Uskrey was more senior and helped shepherd the project, connecting the theoretical insights with practical implementation within Google's research environment. And apparently, he's often credited with coming up with the actual name, the transformer.
Catchy name. Okay, but let's talk about that ripple effect, the authors who left to start major AI companies. This seems like a huge brain drain from Google, but also a massive validation of the paper's impact.
It's incredible when you look at it. Take Aidan N. Gomez. He was actually an intern at Google Brain when the paper was published.
An intern? Wow!
Yeah, contributed significantly to the core ideas and framework. Then, armed with this deep insider knowledge of the architecture that was about to change everything, he goes off and co-founds Cohere.
Cohere, right. Now a major player providing large language models and APIs, directly competing with Google and OpenAI.
Exactly. Building enterprise-focused LLMs, all based fundamentally on the transformer tech he helped create as an intern. Talk about a career trajectory.
Seriously, what about Cillian Jones? His expertise was more on the engineering side.
Yes, Jones was critical for making the transformer actually work efficiently in practice. His focus was on the implementation details, the parallelization strategies, making it run fast on GPUs. That efficiency gain was so crucial.
And where did he go?
He later co-founded Sakana AI.
Sakana AI, okay. What's their focus?
They're exploring novel approaches to machine intelligence, often inspired by nature, like schools of fish, but still very much building on and evolving the core principles of efficient, large-scale models, like the transformer, continuing that mission of optimization.
Okay, one more key departure. Ilya Polasukin. His path was slightly different.
A little different, yeah. Polasukin also had expertise in building large, robust software systems. After Google, he co-founded Near Protocol.
Near Protocol, that's a blockchain platform, isn't it?
It is. But the core focus of Near is building a highly scalable, developer-friendly blockchain. The challenge of designing decentralized systems that can handle massive scale efficiently has a lot of conceptual overlap with the engineering challenges of making giant transformer models work reliably across distributed hardware. Those lessons in scalable systems design are transferable.
That's incredible. So out of the 8 authors on this one paper, you have key figures going on to co-found Cohere, Character.ai, Sakana AI, and Near Protocol.
Yeah. It's like the paper wasn't just a blueprint for AI. It was practically a launch pad for a significant chunk of the next generation of major AI and tech companies. It really underscores how foundational that 2017 work was.
Okay, we spent a lot of time rightly celebrating the transformer and its impact. But, for anyone really wanting to understand this space deeply, we need to add some critical nuance. No architecture is perfect, right? In self-attention, the core mechanism, it has this well-known drawback, a kind of Achilles heel that researchers are still grappling with today.
That's absolutely right. And that fundamental weakness is the quadratic scaling problem related to sequence length. We touched on efficiency, but this is the flip side.
Quadratic scaling, meaning the compute cost grows with the square of the sequence length.
Exactly. Let's make that concrete. If you double the length of the input sequence, say, you go from processing a paragraph to processing 2 paragraphs, the amount of computation required by the self-attention mechanism doesn't just double, it quadruples.
Okay, nuller becomes 2 nullers. Cost goes from $2 to $202, which is $4 4 times the work.
Right. And if you triple the length, the cost goes up by a factor of 9. It explodes very quickly.
And while computation time is one issue, the bigger problem is memory, isn't it? Especially GPU memory, VRAM.
That's the real killer, the practical bottleneck. To calculate self-attention, the model needs to compute and then store that huge attention matrix. The matrix basically holds the similarity score between every single token, query, and every other single token key in the sequence.
So if you have n tokens, that matrix is n by n in size.
Exactly. N squared entries. As the sequence length n grows, as we try to feed LLMs longer documents, entire books, maybe long videos with many frames, the sheer amount of memory needed just to hold that attention matrix in the GPU's VRAM grows quadratically. It becomes astronomical.
And GPUs, even high-end ones, have a finite amount of VRAM.
Right. So this quadratic memory requirement imposes a hard, practical limit on the context window size of almost all current large language models. Why can't you just feed ChatGPT an entire novel and ask questions about it? A big part of the reason is that the attention matrix would become too massive to fit in the GPU memory needed for computation. It hits a wall.
Okay, so this isn't just some theoretical complexity issue. It's the direct, practical reason why LLMs currently struggle with extremely long inputs. And it's driving a ton of current research.
It's arguably the biggest driver of architectural research in large models right now. Everyone is searching for the Holy Grail. How do we keep the power and contextual understanding of attention but escape this crippling 10 to low 2 computational and memory trap?
So what are some of the main approaches? How are researchers trying to make efficient transformers?
There are quite a few directions. One major family of approaches falls under the umbrella of sparse attention.
Sparse attention, meaning not every token looks at every other token.
Exactly. Instead of calculating that full n-by-n matrix, these methods try to be clever about it. Maybe a token only attends to its nearby neighbors in the sequence. Or maybe it only attends to a few key tokens identified as being globally important. Or maybe it uses clever hashing tricks. The goal is to drastically reduce the number of pairwise comparisons you actually need to compute and store.
So you're approximating the full attention matrix, hoping to keep most of the benefits while cutting the cost.
Pretty much. If you can make the number of calculations scale closer to linearly with n, or maybe n log n instead of n squared, you could potentially unlock much, much longer context windows.
Are there other approaches besides sparsity, maybe changing the core calculation?
Yes. Another big area is looking at alternatives to the standard dot product attention and the softmax function. Some methods, often called linear attention or kernel-based methods, try to reformulate the math entirely to avoid constructing that giant n-by-n matrix explicitly.
Okay, trying to get the same result with different, more efficient math.
Right. If these linear attention methods can truly capture the power of attention without the quadratic cost, that would be a massive breakthrough. It's still an active area of research, finding methods that are both efficient and perform, as well as standard attention on complex tasks.
So lots of work on fixing the core attention mechanism. What other big trends are building on or maybe augmenting the original transformer idea?
Well, one huge trend is retrieval augmented generation, or RAG-Bainer.
WAG, right. Heard a lot about that.
The idea here is to kind of outsource the model's knowledge. Instead of trying to bake all the world's facts into the transformer's parameters during pre-training, which contributes to the scaling challenges, you give the transformer access to an external database or knowledge source. When the model needs a specific fact to answer a question, it first performs a quick search or retrieval in that external database to find relevant information. Then, it uses its powerful language and reasoning skills, thanks to the transformer architecture, to synthesize an answer based on the retrieved knowledge.
So the transformer focuses on reasoning and language generation, while the external database handles the factual recall, kind of sidestepping the need for an infinitely large model memory.
Exactly. It leverages the strengths of both components, and it can make models more up-to-date and less prone to making stuff up or hallucinating.
Makes sense. Any other major directions?
The continued push towards multimodal architectures is definitely key. Building systems that can seamlessly process and reason across text, images, audio, video, maybe even other sensor data, all within that unified transformer framework using attention. We're seeing incredible progress there, like with Google's Gemini models. The goal is to move towards AI that has a more holistic understanding of the world, closer to how humans perceive it.
So even as researchers are desperately trying to fix that n-squared scaling issue, the fundamental building blocks laid down in 2017, self-attention, multi-head attention, the parallel structure, they still seem to be the bedrock for all these future directions, whether it's efficient attention, array, or multimodality.
Absolutely. The transformer didn't just define the last, say, 7 years of AI progress. Its core ideas, even if modified or optimized, look set to define the next era as well. It truly was a paradigm shift based on one core insight: ditching sequence for parallel attention.
It really proved that an entire field could be revolutionized just by questioning and abandoning one long-held architectural assumption that sequential processing was necessary for sequential data.
It did. Which leads us nicely.
Right. To our final provocative thought for you, the listener, the attention is all you need. Papers showed that letting go of the sequential processing assumption of RNNs was the key to unlocking massive scale and power via parallelized attention. That solved one huge problem.
But, as we just discussed, it introduced or at least highlighted another major challenge. That 2 complexity, especially the memory cost, which now limits context length.
So the question we want to leave you with is this. What fundamental architectural assumption are we holding on to today? What principle, maybe related to that 2 scaling, maybe related to how we represent information as discrete tokens, or maybe something else entirely? What unseen constraint is limiting the next leap forward in AI?
And what revolutionary paper, maybe being written right now, will be the one to tell us we need to abandon that assumption next to unlock the next level of artificial intelligence? Something to think about as you watch this incredibly fast-moving field continue to evolve.
Definitely something to ponder. Thank you for joining us for this deep dive.